Hey everybody, my name is Gal Engelberg. I am an applied research team lead at Accenture Israel Cyber R&D Labs. My research is focused on AI for cybersecurity and organization impact of cyber risk. I am an Israeli, and we are experiencing a very challenging and difficult times. And I would like you to join me for a moment of silence in memory of those who were murdered in the horrific terrorist attack by Hamas on October 7. Thank you. Okay, I will be speaking today about how we use large language models and knowledge graphs in order to generate cybersecurity countermeasures in an automatic way. I will present the approach, and then I will highlight the main steps that we're taking in order to apply it. Okay, so first of all, regarding the motivation. Cybersecurity frameworks often provide generic guidelines of how to remediate cybersecurity issues. However, these recommendations are often generic and focus on what to do, nor on how to do it. Okay, and always an additional knowledge is required in order to deploy these actions and remediations in a concrete use case on a specific environment. And therefore, we state that there is a need to automatically create use case specific instructions. Given that need, we formalize the following problem statement. Given a description of an issue, a vulnerability that was observed in a specific system over a specific entity, we would like to understand what digital artifacts affected by that issue, then what countermeasures should be deployed in order to mitigate the risk over the digital artifacts, and finally, to generate what concrete steps should be performed in order to deploy each countermeasure. In order to do so, we base our solution over the Defend Knowledge Graph, which is a fantastic project by MITRE. The Defend Knowledge Graph is composed of three components. The first one is the digital artifact ontology, which represents digital artifacts and their relations. Each digital artifact is mapped to an offensive model and a defensive model. An offensive model stands for different techniques that an attacker can perform in order to compromise the digital artifact. And the defensive model stands for the different defensive techniques that the defender could do in order to protect the digital artifact. Okay, this is a very nice example. Exemplified by an executable binary. You can see on the left that executable binary has hierarchical relations within the knowledge graph. Executable binary is a executable file, is a resource, etc. We can see in the graph other relations between digital artifacts to each other. We can see that executable binary contains image code segment, for instance. Okay, here on the right, you can see multiple countermeasures that are mapped to executable binary. Okay, we can see that file could be spoofed by a decoy file countermeasure. And on the other hand, we can see here on the right that executable binary could be modified by binary padding, which is an attack technique. This is the approach in a nutshell. We take a vulnerability description as an input, and then we first extract the digital artifacts out of the text automatically. Okay, we get digital artifacts instances and types. We do this based on the defend-based grounding. We represent the defend knowledge graph via Neo4j using the NeoSemantic library. Okay, and then we use elements extracted from the defend knowledge graph to ground the prompts within this task. Then we use again the defend knowledge graph representation within Neo4j in order to extract the corresponding countermeasures for each digital artifact instance. Then at that point we have the digital artifact instances and the corresponding countermeasures. And then we search for relevant documents using semantic search-based grounding. Okay, so basically we are searching different cybersecurity playbooks and documentations for relevant information that we can use in order to generate the use case specific guides. So eventually, after we've done all of these steps, we take the digital artifact instances, their corresponding countermeasures, and the top K documents extracted from the cybersecurity playbooks, and we run a generation task in order to create the step-by-step guide. Okay, so after we overviewed the approach in high level, I would like to deep dive into each step. Okay, so the first step is the digital artifact extraction from text. We take here a vulnerability description and we run two main tasks. The first task is to extract the affected entities. Okay, we do this based on analyzing the vulnerability description. And then we take the affected entities, and the task is to classify them according to the defend taxonomy. In order to do so, we search within the Bing Search API for the top K descriptions. We feed this together with the possible classes that we extract from Neo4j. And then we classify all of the affected entities according to the defend taxonomy. And the output here is digital artifact instances and their types. On preliminary evaluation, we saw that we have a recall of 70%, a precision of 40%, and an accuracy of more than 1/8 of 75%, which is pretty moderate results according to the fact that defend holds hundreds of digital artifacts and 60 digital artifacts categories. Okay, so now after we extracted the digital artifact instances and types, we query the defend knowledge graph using a cipher query in order to extract all of the corresponding countermeasures. We're using the following cipher query. And then at that point, we have the digital artifact instances, okay, their types, their countermeasures. And given that information, we would like to search for relevant documents. We do this in two steps. The first one is an offline step, where we index playbooks and documents in a vector database. We take the documentations, we embed them, we store them in a vector DB. And then in the online phase, we search for the relevant documents. We take the vulnerability description, the entity, and the countermeasure type, we concatenate them, we embed them, and then we search within the vector database and return top K matches. And finally, after we've done all of the previous preliminary steps, now we generate the guides. Okay, we take the context, the vulnerability description, the entity, the countermeasure, the relevant documents that we extracted on the previous step, and we run a task to generate a step-by-step instruction of how to apply a countermeasure to the product based on the provided documents. The output of this step is a detailed guide. Then we run another summarization task in order to simplify the guide to further senior users. Okay? And this is an example of the approach. This is a vulnerability description of a vulnerability over AWS Cloud Development Kit that has two libraries that constructs two roles, okay, that have overly permissive trust policy. Now, on the first step, we ask what digital artifacts affected by this issue, and we see that we extracted correctly the 3 digital artifacts, the component and the libraries, and we classify it according to the different taxonomy. You can see it on the right, software, platform, etc. And then for each digital artifact, instance, and classes, we extracted the countermeasures. In that case, you can see here software inventory, software update, asset vulnerability enumeration, and so on. And on the next step, we extracted the detailed guide for software update of AWS Cloud Development Kit. You can see here that there are explicit steps, concrete steps of what to do, including code snippets and so on. Okay, this detailed guide is being simplified to further senior users. And you can see here that the corresponding steps are represented here in a much more abstracted manner. Okay, so the key takeaways of what I presented today are that the approach can generate a use case specific defensive guidelines given a vulnerability description. We saw that LLMs can classify entities according to the provided taxonomy with a moderate accuracy, and we did not use any fine-tuning here, which is pretty amazing. And finally, we can control the LLMs without fine-tuning by using grounding based on knowledge graphs and documentation. We saw that on multiple steps when we queried Neo4j and entered the results as context to the prompt, and we've done the same with the documentations. Thank you very much. I can answer any questions.